In our last lecture, we have discussed on the based linear unbiased estimator or BLUE. A based linear unbiased estimator is that unbiased estimator which has the minimum variance among all linear unbiased estimators of a given parametric function. In the present lecture, we shall discuss on the uniformly minimum variance unbiased estimators. A uniformly minimum variance unbiased estimator is that unbiased estimator which has the minimum variance among all unbiased estimators for a given parametric function. Now in literature, there are so many methods of deriving a uniformly minimum variance unbiased estimator. In the present lecture, we shall discuss a method of deriving a uniformly minimum variance unbiased estimator. The method is called the method of covariance. We shall also discuss some examples where one can apply the method of covariance for deriving a uniformly minimum variance unbiased estimator. In this lecture, first we shall define a uniformly minimum variance unbiased estimator, which is abbreviated as UMVUE. Let g theta be an estimable function of the unknown parameter theta, and UG be the class of all unbiased estimators of g theta with finite variances. That is, UG equals to set of all t such that expectation of t equal to g theta and variance of t is finite for all theta belongs to script theta. An estimator capital T belongs to UG is said to be a uniformly minimum variance unbiased estimator of g theta if variance of t is less than equals to variance of t dash for all theta and for all t dash belongs to UG. Next, we shall discuss a method for determining a UMVUE. This is called the method of covariance. Let U naught be the class of all unbiased estimators of 0 with finite variances. That is, U naught equals to the set of all Hx such that expectation of H equals to 0 for all theta and variance of H less than infinity for all theta. Then an estimator capital T belongs to UG is a UMVUE of g theta if and only if covariance T, H equals to 0 for all theta belongs to script theta and for all H belongs to U naught. That is, T is uncorrelated with every unbiased estimator of 0. Now, we shall prove this method of covariance. First, we shall discuss the only if part. Let U belongs to UG be a UMVUE of g theta and T star be any other statistic such that T star equals to T plus lambda into H, where H belongs to U naught and lambda is a fixed constant. Therefore, expectation of T star equals to expectation of T plus lambda into expectation of H, which is equal to g theta for all theta, which implies that T star belongs to UG. Since T is a UMVUE, variance of T is less than equals to variance of t star for all theta. Now variance of t star is equals to variance of t plus lambda square into variance of h plus 2 into lambda into covariance t comma h. This implies lambda square variance of h plus 2 lambda into covariance t comma h is greater than equals to 0 for all theta. We write this as equation 1. Now, if covariance t comma h is not equals to 0 for some theta naught belongs to script theta, then we choose lambda equals to minus covariance t comma h under theta naught whole divided by variance of h under theta naught. Then for theta equals to theta naught, the LHS of 1 becomes lambda square into variance of h under theta naught plus 2 into lambda into covariance t comma h under theta naught, which is equals to minus covariance square t comma h under theta naught whole divided by variance of h under theta naught, which is less than 0. This contradicts 1 for theta equals to theta naught. Hence, covariance t comma h is equals to 0 for all theta belongs to script theta. Now we discuss the if part of the proof. Suppose T belongs to UG be an estimator of g theta such that covariance under theta t comma h equals to 0 for all theta belongs to script theta and for all h belongs to u naught. Let T star be another unbiased estimator of g theta. Let us define h star equals to t star minus t. Then expectation of h star equals to expectation of t star minus expectation of t, which is equals to 0 for all theta, which implies that h star belongs to u naught. Then covariance t comma h star equals to 0 for all theta, which implies that covariance t comma t star minus t is equals to 0 for all theta. Now, variance of t star is equals to variance t star minus t plus t, which is equal to variance of t star minus t plus variance of t, because covariance t comma t star minus t is equals to 0. Since variance of t star minus t is greater than equals to 0, it follows that variance of t star is greater than equals to variance of t for all theta. Since t star is arbitrary, t has the minimum variance among all unbiased estimators of g theta, that is, t is a UMVUE of g theta. Let us consider some examples. Example 1. Let x1, x2 up to xn be IID normal random variables with mean theta and variance 1, where theta is unknown. Suppose we want to find a UMVUE of theta. The joint PDF of x1, x2 up to xn is given by f theta x equals to 1 by 2 pi to the power n by 2 into e to the power minus half into summation over I from 1 to n xi minus theta whole square. Xi belongs to real line for all I. Let H be an unbiased estimator of 0. That is, expectation of H equals to 0 for all theta, which implies integration over r to the power n hx f theta x dx equals to 0 for all theta. Differentiating with respect to theta, we get integration hx into summation over I from 1 to n xi minus theta into f theta x dx equals to 0 for all theta, which implies integration hx into x bar minus theta into f theta x dx equals to 0 for all theta, which implies integration hx into x bar into f theta x dx equals to 0 for all theta, since expectation of h equals to 0 for all theta. Thus we get expectation h into x bar equals to 0 for all theta. Also, expectation of x bar is equals to theta for all theta. Hence, x bar is the unbiased estimator of theta, which is uncorrelated with every unbiased estimator of 0. By the above result, x bar is the UMVUE of theta. Next, we consider another example. Example 2. Let x be a random variable with PMF. F theta x equals to theta if x equals to -1 equals to 1 minus theta whole square into theta to the power x if x equals to 0, 1, 2 up to infinity, where 0 less than theta less than 1. Theta is unknown. Suppose we want to find the parametric functions g theta which admits of a UMVUE, and also to find such estimators. Let hx be an unbiased estimator of 0. That is, expectation of hx is equals to 0 for all theta, which implies theta into h minus 1 plus summation over x from 0 to infinity hx into 1 minus theta whole square into theta to the power x is equals to 0 for all theta, which implies summation over x from 0 to infinity hx into theta to the power x is equals to minus theta into h minus 1 whole divided by 1 minus theta whole square, which is equals to minus summation over x from 0 to infinity h minus 1 into x into theta to the power x for all theta by expanding 1 minus theta whole square. Now, comparing the coefficients of theta to the power x for x equals to 0, 1, 2 from both sides of the above identity, we get hx equals to minus x into h minus 1 for x equals to 1, 2 and h0 is equals to 0. We write this as equation 1. Let t be a UMVUE of g theta. Then t is uncorrelated with h. Therefore, expectation t into h is equals to 0 for all theta. Hence, by a similar argument as before, we get Tx into Hx is equals to minus x into t minus 1 into h minus 1 for x equals to 1 to up to infinity, and t0 into h0 is equals to 0. We write this as equation 2. Comparing equation 1 and equation 2, we get Tx equals to t minus 1 for x equals to 1 to up to infinity, and t0 is arbitrary. Tx is thus defined is the UMVUE of its expectation. Now, expectation of t equal to g theta for all theta implies g theta equals to 1 minus theta whole square into t0 plus t minus 1 into 1 minus theta whole square, which implies g theta equals to c1 into 1 minus theta whole square plus c naught, where c naught equals to t minus 1 and c1 equals to t0 minus t minus 1. Hence, an estimable function g theta will have the UMVUE if it is of the form g theta equals to c1 into 1 minus theta whole square plus c naught, and the UMVUE of g theta is given by Tx equals to c0 plus c1 if x equals to 0, and it is equals to c0 if x equals to minus 1, 1, 2 up to infinity. Note that if we take g theta equals to theta, then it cannot be put in the above form, and hence there does not exist a UMVUE of theta. Though there exists an unbiased estimator of theta which is given by Tx equals to 1 if x equals to minus 1 and Tx equals to 0 if x equals to 0, 1, 2 up to infinity. Next, we consider another example. Example 3. Suppose x follows rectangular distribution with parameters theta and theta plus 1. We shall prove that there does not exist any non-constant function of theta which admits of a UMVUE. To prove this, suppose g theta is any non-constant function of theta. Let hx be any unbiased estimator of 0, that is, expectation of hx equals to 0 for all theta, which implies integration theta to theta plus 1 hx into dx equals to 0 for all theta. Differentiating both sides with respect to theta by Leibniz theorem, we get h theta plus 1 minus h theta equals to 0 for all theta, which implies h theta plus 1 equals to h theta for all theta. We write this as equation 1. Let Tx is a UMVUE of g theta. Then Tx is uncorrelated with h. Therefore, expectation h into t is equals to 0 for all theta. By a similar argument as before, we get h theta plus 1 into t theta plus 1 is equals to h theta into t theta for all theta. We write this as equation 2. Comparing 1 and 2, we get t theta plus 1 equals to t theta for all theta. Now, expectation of t is equals to g theta for all theta, which implies integration theta to theta plus 1 tx dx equals to g theta for all theta. Differentiating with respect to theta by Leibniz theorem, we get t theta plus 1 minus t theta equals to g prime theta for all theta, which implies g prime theta equals to 0 for all theta, which is a contradiction to the fact that g theta is a non-constant function of theta. For example, if g theta equals to theta, then an unbiased estimator of g theta is x minus half, but there does not exist any UMVUV of theta. In our present lecture, we have seen that an unbiased estimator will be the uniformly minimum variance unbiased estimator if and only if it is uncorrelated with every unbiased estimator of 0. In our lecture, we have applied the method of covariance in finding the UMVUV for the parameter theta in normal population with mean theta and variance 1, but in practice we can apply this method also on other distributions. We have also seen that in some cases there will be no uniformly minimum variance unbiased estimator, though there exists a unbiased estimator for a given parametric function.